Since the beginning of recorded history, men have gone underground to mine the minerals and metals needed for the growth of civilization. During the exploration and exploitation of these natural resources, their lives were endangered by the hazards of falling ground. They learned from bitter experience not to depend on the natural self-supporting quality of overhead rock to protect them from bodily injury. They found that openings made in the earth for the removal of ore set up unbalanced stresses in the surrounding roof and walls, causing the top of the opening to sag until a point was reached where the overlying rock either supported itself or it fell, causing a cave-in. To compensate for these unbalanced stresses that caused the collapse of mine openings, a means of ground support was needed. The most practicable and readily available material was wooden posts, so timbering became the principal or conventional means of maintaining underground openings. To determine the amount of support needed for their protection, early miners worked largely by rule of thumb and timbered by trial and error. Even today, timbering to prevent collapse of mine workings is still governed by experience. Largely from the dislodgement or collapse of inadequate timbering, the number of fatal and serious injuries from fall-of-ground accidents also increased as the mining industry continued to grow. With these occurrences, other methods of ground support were developed. One of these, rock bolting, proved most successful. The effectiveness of rock bolting is shown by this installation in a lead mine at St. Joseph, Missouri. These bolts, including those interlaced with continuous bearing plates of channel iron, were installed over 60 years ago. The bolted ground is as firm and sound today as it was the day the bolts were installed. As methods of ore extraction changed from hand loading to mechanical continuous mining, more and more mines began using rock bolts as their chief means of ground support. Besides providing safe and adequate ground support, rock bolting allows work to be carried on without the interference of standing or overhead timbers. More room is left for mobile equipment and haulage vehicles. They can be maneuvered easier and safer in entries where bolts replace timbers, especially at intersections. In high workings where it's difficult, if not impossible, to use timbering, installing rock bolts to support the back is particularly advantageous. The absence of timbers obstructing the mine openings also contributes to better ventilation. And it also has been found that bolts are less likely to be dislodged by blasting than conventional timber supports. In some mines, due to the nature of the earth's strata or surrounding rock formation, different reinforcement materials are used in conjunction with the bolts to provide a larger bearing surface to help prevent cracking and spalling of the rock. In such situations, rock bolts may be supplemented with wooden blocks, wire mesh, steel landing mats, or iron channels. Sometimes special bolting patterns are required for wide spans, such as at intersections, and under certain conditions it may be advisable to strengthen the regular pattern by adding more bolts, or by installing extra long bolts to effectively solve a difficult ground control problem. The exact length of the bolts will depend on mining conditions and geologic structure. There are many different types of bolts or bolt anchors being manufactured, but generally they can be grouped into two main categories. The first is the conventional or plug type anchor, which is used mostly in hard rock. The second is the bale type, which is favored in softer rocks. Also needed in conjunction with the bolts is a washer or plate to act as a bearing surface between the bolt head and the exterior surface of the rock. These plates allow the proper tension to be applied to the bolt to effectively anchor it in the hole. This cutaway section of an ore body and surrounding strata will better explain the principles of rock bolting. When a mine tunnel or opening is made in the earth, the overlying weight or forces that act upon the stratified rock deposits cause the immediate roof to sag. If rock bolts and bearing plates are installed in the mine roof, the layers of stratified rock deposits are compressed and a strong consolidated beam is formed. Now very little sag occurs. This demonstrates the principle of beam building. The simplest method of rock bolting is by suspension. In this method, the roof is held up or suspended by securing the loose pieces of rock to the solid ground above it. The bolts must be long enough, strong enough, and sufficiently anchored into the solid ground to support the weight of the loose roof. In non-stratified rock formations or in openings that are largely self-supporting, such as arched openings, rock bolts are installed in a radial direction. These bolts extend through the non-stratified or fractured rock and are anchored in the surrounding ground. A zone of radial compression in the rock is created around the opening by the tension in the bolts. Installed in a systematic pattern, the bolts form a series of rigid blocks by consolidating the fragmented formation around each bolt. What would correspond to a natural arch is formed by the blocks keying together. The bolted zone is then more capable of accepting a larger load and is more self-supporting. The keying effect can be demonstrated by this model. The metal frame has been filled with crushed rock, which represents the non-stratified fractured zone of a mine roof. The rock has been bolted together with miniature rock bolts and bearing plates. The bolted layer of crushed rock not only supports itself, but also the weight of an additional bucketful of rock. To further increase the effectiveness of rock bolts, a bolting pattern should be adopted, one that is suitable to existing mining methods and conditions and the physical properties of the rock. With a uniform bolting pattern, interaction between adjoining bolts will be continuous and far more effective in controlling unknown conditions than random spotting of individual bolts. The safety of miners who must work in newly opened areas or places just recently blasted is greatly increased if rock bolts are installed as soon as possible after the opening is made. Rock bolts are especially effective when they're installed directly after blasting, where within a short space of time they can be exerting a stabilizing pressure on the loosened rock surface while preventing air slacking. Before starting the drilling and bolting cycle, it's important to bar down loose rock that could possibly fall during bolting operations. This is to protect not only the bolting crew, but any other workers in the area. Bolt installation begins by drilling holes for the bolts according to the approved bolting plan. The drills used should be equipped with suitable dust collectors and water dispensing devices to control drill dust, thereby helping to prevent respiratory health hazards such as silicosis. Hole diameter must be closely controlled with the expansion type rock bolt. The hole size must be close to the manufacturer's recommended hole diameter for the anchor used. It's especially important if the bolts are supporting a steep wall or rib. The exact hole depth, however, is not as important, since the bolt need not bear against the back of the hole to anchor successfully. Expansion type bolts in widespread use today are the 3/4 inch and 5/8 inch diameter, grade 55 high strength, or grade 75 extra high strength steel. The expansion shell bolt is simple to install by hand, compressed air, or electrical power. It is anchored through the compressive action of the shell expanding against the inside wall of the drill hole as the threaded, tapered plug is screwed down into it by the rotating bolt. After the bolt is tightened with an air-operated impact wrench or bolting machine, the torque is checked to ensure that the bolt is properly tensioned. Either hand-operated or electronic digital torque indicators are used. The amount of tension should be sufficient to bind the strata or tie the rock surface to competent ground, but it must not exceed the yield point of the bolt. Tension applied at the time of installation must be maintained if the rock bolts are to be effective. Periodic checks should be made. A change in torque reading will indicate a proportionate change in tension of the bolt. The bolt must then be retightened as necessary to maintain the proper torque or eliminate the loss of further tension. Polyester resin rock bolting has come into wide use as the cost of resin has been reduced and improved installation techniques have been developed. Hole depth and hole diameter are important for correct resin bolt installation. The hole depth should be no more than 1 inch deeper than the length of the steel bolt, and the hole diameter should be 1/4 inch larger than the bolt diameter. Roof bolts commonly used for resin bolting consist of headed rebar, threaded rebar, or steel stock with deformations embossed along the length of the bolt. The resin and its catalyst are contained in a single plastic tube separated by either a plastic membrane or by a thin film of reacted resin and catalyst. Inserting and rotating the steel bolt through the column of resin in the drill hole mixes the catalyst with the resin. The drill or bolting machine then holds the bolt in place until the resin sets. The advantages of resin bolting include a continuous bond along the length of bolt, concentrated restraint along a short section of bolt when fractures try to develop, complete water sealing of the bolt hole, and increased shearing resistance to lateral roof movement. Even if some section of a resin bolt breaks, the roof is still reinforced along the unbroken sections of the bolt. Correct bolt length and the anchor capacity of a particular horizon in the rock are usually determined by comparative pull tests and by trial installations. The test procedure consists of drilling the hole, installing the bolt as it normally would be, but with a pulling collar added, and then pulling the bolt with a hydraulic jack assembly and measuring the pulling load and bolt head movement. Readings are taken from the dial gauge at different pulling loads until the load reaches a point where the dial gauge shows continuous movement of the bolt head with no additional increase in load. The point of anchorage failure or permanent stretching of the bolt is determined by plotting the bolt head movement against the pulling load setting. Several pull tests may have to be conducted to determine the best anchor shell and the best anchorage horizon. A torque tension test must also be conducted to determine how many pounds of tension are imposed on the bolt per foot-pound of applied torque. The test is relatively simple in that the load on the bolt is measured with a hydraulic or electrical load cell. It is vitally important that proper torque setting be constant on all bolting devices, because improperly torqued bolts can create assumed safety conditions that are dangerous. The torque on the bolt is simultaneously measured with a torque wrench or digital torque readout. The torque tension ratio is then obtained by dividing the load on the bolt by the torque. Over the years, rock bolting has proven to be a lifesaver, both in the miner's individual safety and to the economic stability of the mining industry itself. Experience has demonstrated that bolts are less likely to be dislodged by blasting than timbers would be, and some deposits previously too costly to mine with timbering can now be mined economically with the use of rock bolts. When rock bolts are used, a miner's work can be carried on more safely and efficiently without the interference of standing or overhead timbers, and the absence of timbers obstructing the mine openings contributes to better ventilation. And while it can be considered one of the great advances in modern mining, much development and research remains to be done. No formula can take into consideration all the variables which might be encountered in an underground opening. It's up to management to develop an effective ground control program and to install a carefully planned bolting pattern to fit the specific mining conditions of their mine. And it's then up to both miners and management to follow this ground control program faithfully in order to make their mine a healthier and safer place in which to work.